Friends,
Good afternoon, sir.
Good afternoon, sir.
Good afternoon,
good
sir.
good afternoon, all of you. So, let us try to summarize what we have discussed in the last class and then continue with our discussion. Can anyone say what we have discussed in the last class? What are the major points? No one? Yes, very good. Metallic bonding and
Enthalpy of atomization and exceptions in D block.
very good. So, last class we have just introduced the concept of D block elements. We have looked at the position of D block elements in the periodic table, and we know the D block elements will be categorized into 4 series, 3D series, 4D series, 5D series and 6D series. In that context, we have just looked at what are the different series we have, written their general electronic configurations, and if you look at the D block elements, they are also called as transition elements except your 12th group, that is the zinc group. Why? Because in the zinc group, you do not have any unpaired electron in the ground state or in the excited states. And then if we look at what type of bonding is present, metallic bonding exists in all the metals, and this metallic bonding is actually directly proportional to the number of unpaired electrons. So as we go from left to right in a particular series, the number of unpaired electrons increases. With increase in number of unpaired electrons, stronger metallic bonding should be there. If metallic bonding is stronger, melting point should be stronger or highest. Similarly, enthalpy of atomizations, the enthalpy of atomizations, they are going to be increasing in this manner. And we have metal kernels. Metal kernels are Mn plus ions, that is the species which are obtained after the loss of outermost electrons. Right, students, these are the different points which we have studied. And after that, we have written the electronic configuration. Let us proceed with this concept. These are the exceptions which you are going to see. In the 3D series, we have exception of chromium and copper. In the 4D series, you have exception of these elements. In the 5D series, you have exception of platinum and aurum. In the 6D series also, you have exceptions. So before going into the exceptions of electronic configurations, let us look at the graphs of melting point and enthalpy of atomization, then come back to your exceptions. So this melting point, if you try to figure out, last class itself we have told you, like metallic bonding is directly proportional to number of unpaired electrons. Number of unpaired electrons. If the number of unpaired electrons increases, metallic bonding should be high. Why? Because the metal kernels and the electrons, they are going to have stronger electrostatic force of attraction. So if metallic bonding is high, the melting point would be high or not? Yes or no? Melting point of a metal, if you talk about melting point of a metal, that is again directly proportional to metallic bonding. Metallic bonding. How you can say this, sir?
Yes.
Because, yes, Harishri?
Yes, sir.
Yeah, any doubts?
No, sir.
No, right? Okay, fine. So we have a metal, students. In that metal, we have different crystal lattice sites. At all the crystal lattice sites, we have metal ions, and you have free electrons moving throughout the metal, and you have free electrons moving throughout the metal. Metallic bonding means what? The electrostatic force of attraction between the metal kernel and all the free electrons. If that is stronger, if that electrostatic force of attraction between the metal ion and all the free electrons, if that is stronger, what is going to happen? That means the metal want to be in that crystal state only. The metal wants to be in that crystal state only. What is melting point? Melting point is the temperature at which the melting of the metal starts. What do you mean by that? That means at which the solid state of that particular substance is going to be the liquid stage. Melting is going to happen. If melting is going to happen, can I say that melting is going to disturb the intermolecular metallic bonding? Or you can say metallic bonding, if it is disturbed, the solid will not be present now. It will be coming into the liquid stage. So melting happened. So stronger the metallic bonding, higher temperature I have to give. So higher will be the metallic bonding, or higher will be the melting point. Yes or no? Greater the metallic bonding, greater the electrostatic force of attraction between the metal ion and the free electrons. If that is stronger, I need to provide a very high amount of thermal energy to break that attraction. That means my melting point would be high. So what about the order of melting point, students? If you look at the graph, melting point if you take on y-axis, atomic number you take on the x-axis. So as increasing in the atomic number, what is happening? The number of unpaired electrons increases. But for manganese, we have a decrease in melting point. Why? For manganese technetium, for D5
Different
systems,
lattice.
yeah, very good. For D5 systems, we have different lattice structures, and also their electronic configurations are stable. Their electronic configurations, that is D5 configuration, is stable by itself. So it won't go into the metallic bonding greatly. Yes or no? And also their electronic configurations were quite stable. Were stable. So you have increase in the number of unpaired electron, you will be having increase in the melting point. For the D5 system, decrease you can see. After that, again you have seen the increase in the melting point as you see the atomic number increase. This is for 3D series. Similarly, for 4D series and 5D series also we have same scenario. Among 3D, 4D, 5D series, which will have stronger metallic bonding?
5D.
5D, why?
More number of electrons.
Yeah, Nandana, I could not hear you. Can you repeat?
So there's more number of unpaired electrons in the 5. Yeah.
More number of unpaired electrons, or I am considering the same element like titanium. Like in the titanium, how many unpaired electrons are there? Similarly, in that particular group only, whatever the element I have, I will be considering. Unpaired electrons are same, but easily the electrons are lost. That is the point.
Yes,
Okay.
sir. Okay.
Order of metallic bonding will be 5D greater than 4D greater than 3D, because the electrons are easily lost. Why? Because the electrons are far from the nucleus. So if electrons are easily lost, we get the metal kernel easily, and all the free electrons are present. So obviously the electrostatic attraction would be high. So in the 5D series, we have stronger metallic bonding when compared to 3D series, when compared to 4D and 3D series. So 5D will be greater, then 4D, then 3D. If this is the order of metallic bonding, what should be the order of melting point? Same order or not? Because higher the metallic bonding, higher will be the melting point. That is why you have seen. These are very logical points, students. Why? Because from these metallic bondings only we indicate enthalpy of atomizations. From the enthalpy of atomizations only we indicate electrode potentials. From the electrode potentials only we say that a particular element is a stronger oxidizing agent or a stronger reducing agent. All those are interlinked. Okay, that's why I'm explaining in detail. Listen carefully. For a 5D series element, we have more metallic bonding when compared to 4D. For a 4D series element, we have more metallic bonding when compared to 3D. Because for 5D, electrons are easily lost. That means the metal kernel attracts the electrons easily. That means you have stronger electrostatic force of attraction, which means stronger metallic bonding. So metallic bonding order will be equivalent to melting point order. Melting point has same order, right? Is everything clear so far with the graphs?
Yes,
Yes,
sir.
sir.
Yes, very good. Heat of atomization, similar graph can I expect or not? Can I expect similar graph? Enthalpy of atomization means the energy required to break the metallic bond. That means greater the metallic bond, more amount of energy have to provide. So enthalpy of atomization means the energy required to break the metallic bond and bring out the metal atom. Stronger is the metallic bond, more will be the heat of atomization. More number of unpaired electrons favors the formation of metallic bond. The third point, which are same things. In case of manganese, due to stable N-1D and Ns configurations, metallic bonding is weak. That's what we have said earlier. In the case of D5 elements or D5 electronic configuration, because of stable electronic configurations and different also different crystal structures. Different crystal structures. In the case of manganese, due to stable electronic configurations and also different crystal structure, the metallic bond is weak. Manganese and zinc has the lowest heat of atomization due to stable electronic configuration and are not available for metallic bonding. So that is what you can understand. So from these points, can I draw the graph again? Same points. Stronger metallic bonding means very difficult for that metal to melt. So melting point is high. Stronger metallic bonding means very difficult for that metal to lose the metal atom. That means enthalpy of atomization is high. Again, both all these three, enthalpy of atomization, melting point, metallic bonding, all these three are directly proportional to number of unpaired electrons. All these three are directly proportional to number of unpaired electrons. Greater the number of unpaired electrons, greater is the metallic bonding, greater is the enthalpy of atomization, greater is the melting point. Exception for D5 electronic configuration. Why? Because they have different crystal structure and obviously they have stable electronic configurations. Same thing, 3D series, this is 4D series, this is 5D series. This is the same graph or not? Similar to that of metallic bonding and melting point. Is that clear, students? These graphs?
Yes, sir.
Yes,
Yes.
sir.
Yes, sir.
Very good now. So now let us start with some exception cases with respect to electronic configuration. You have some tricks to remember these electronic configurations. In the 3D series, you have elements from scandium to zinc. Where do you have exceptions? You have exceptions at chromium and copper. In the 4D series, you have yttrium to cadmium. You have many exceptions in the 4D series, like in the D3 configuration, D6, D9, they do not exist. In the 5D series also, you have D8 do not exist. Let us now look at all the electronic configurations of all the elements in 3D series, 4D series and 5D series. Wherever the exception is there, you have to note down carefully. Yeah, in the 3D series, scandium, argon 3D1 4s2, titanium, argon 3D2 4s2, vanadium, argon 3D3 4s2, chromium you have exception. Manganese, iron, cobalt, nickel, copper you again have exception. Why these exceptions arise? Can anyone say? Why are the exceptions present in the electronic configurations of D block elements?
They offer more stability.
Yeah, sure. Prachi says they are for more stability. Any other reason? Like how I can transfer the electron from 4s to 3d? The reason for 3d5 is more stable, that's fine.
Less energy gap.
Yes, very good. These exceptions can be understood, by the less energy difference between ns and n minus 1d subshells. Write down this point, very, very important, students. These exceptions, whatever the exceptions you are remembering, they are arising because of more stability, because 3d5 half filled, 3d10 fully filled, more stable electronic configurations. But it doesn't mean like if there is a stable electronic configuration, the electron has to excite. The electron can excite only if the energy difference is very low. The 3d and 4s, this is ns, this is n minus 1d. Between ns and n minus 1d, the energy difference is less. That is why the electron can excite. That is why you can have this exceptional electronic configuration. Write down this. All of you note down this. Just note down where you have the exception. Chromium and copper, you have the exception cases. If you are done with this noting out the exception parts, please let me know. I'll proceed. All these d block element students, they are also have a tendency to form complexes. After this d and f blocks, we are going to start complex compounds or coordination compounds. There you should understand why a d block element is easily forming the complex. There are a lot of complexes that chemistry is slightly different from your chemical bonding. So how it is different, all those things we are going to study. But to understand that complex compounds, to understand those complex compounds, these electronic configurations of d block elements and these exceptional properties of d block elements are useful. Done with the noting part or not?
Yes, sir.
Yes. Look at the 4D series element, students. Yttrium to cadmium, you have exceptions. 4D1 5s2 no exception, 4D2 5s2 no exception. Here you can see 4D4 5s1. You know ns and n minus 1d has less energy difference. ns and n minus 1d has less energy difference. So electrons can excite from the ns to n minus 1d, that is known. But if you look at niobium, krypton 4d4 5s1. Yes or no? You have two electrons. So you can write 4d3, you can write 4d3 5s2 for niobium, and also you can write 4d4 5s1. The correct electronic configuration is 4d4 5s1. You can say, sir, earlier you said that chromium has an electronic configuration of 4s1 3d5. So there you can say 3d5 is more stable because of half-filled electronic configuration. But here, why you are writing the 44? 44 is not half-filled, no? Then from where you are getting the motive to write a 4d4 5s1 instead of a 4d3 5s2? Are you understanding the question or not? We can simply write 5s2 43 for this niobium, but the actual electronic configuration is 5s1 44. Why we are writing 5s1 44? Even 44 is not the half filled. Can anyone say? Write down this. 4d4 5s1. This is stabilized by. This is stable when compared to 4d3 5s2 due to more exchange energy. Due to more exchange energy. Exchange energy lost means stability gain. Exchange energy lost means stability will be gained. So then you have molybdenum 4d5 5s1. So these are all the exceptions. These are all the exceptions. 4d4 5s1, 4d5 5s1, 4d6 5s1, 4d7 5s1, 4d8 5s1. Write down these electronic configurations of 4d series elements where you have 5s2 in first two elements and the last element only. Yttrium, you can remember like this. Yttrium, zirconium will have 5s2. And the last elements, cadmium will have again 5s2. Remaining all will be having 5s1 except your palladium. You don't go with the D electronic configurations. Yes, Nandana.
Sir, in for neurobium, you said 4d4 has more exchange energy. That's why that's the configuration. Sir, why isn't this applicable for the 3d3 and 5s2? Why can't we write as 3d4 and 5s1, 4s1?
Yeah, that's what, no? So very good question, Nandana. So why can't it applicable to 3d3, 4s2 and 3d4, 4s1? So if you look at the 3d subshell, the 4d subshell and the 5d subshell, what happens when you go on away from the nucleus in the increasing shells? First shell, second shell, third shell, fourth shell, fifth shell. If you go on with the increasing, the D subshell is going to be having electron density more dispersed or not? What is the orbital d orbital shape? The d orbital shape is s orbital is spherical in nature, p orbital is dumbbell, d orbital double dumbbell, f orbital complex. That means in s orbital the electron density is present in a spherical manner. In the p orbital we have electron density in present in a dumbbell manner. So dispersion happened. Dispersion means spreading out. In the d orbital it is in double dumbbell manner, more spreading out. Understanding these points or not? The electron
Yes,
density
sir.
is more spread out. This is the shape of d orbital, that's fine. But if you compare the 3d subshell and the 4d subshell, which has a larger size, 3d and 4d, 3d and 4d, if you try to compare, which has larger size?
4d?
Obviously 4d. Obviously
Yes.
4d. So d orbital is dispersed in shape. 3d and 4d, if you compare, 4d is larger in shape. So where is the electron density dispersed greatly? In the 3d or in the 4d?
And the 4d?
On the 4d, because it is larger in size. So because of 4d, because of large size of 4d, what you are going to have is, when you study the energy difference between 4d and 5s, it is even smaller when compared to the energy difference between 3d and 4s. So the electrons are easily transferring from the 5s to the 4d subshells very easily. This can be understood because of very less energy difference between 4d and 5s when compared to the energy difference between 3d and 4s. Understood now?
Yes, sir. Yeah.
Can I apply the same logic in 5d? So you may ask a question, sir, in 5d series, the more dispersion is there, then can I say the 6s and 5d can be going to easily? So in all the cases, you can write the electronic configuration. Can I say like that? No. Why? Because whenever I go to the 5d series, there I have inner 4f electrons also. Yes or no? 4d series means which period? Fifth period. In the next period, in the sixth period, I will be having f orbital or f subshells filled. Yes or no? Because of f
Yes.
subshell field, you do not have the same electronic configurations or same exceptions in the 5d series. In the 5d series, write down. So that is why it is important to know where the exceptions are high and why it is so.
Yes,
So
sir.
between, okay, fine, okay. So between 4d and 5s, the electrons can be easily transferred when compared to the electron transferring happening between 3d and 4s. That is why you can say 4d4 5s1 is the electronic configuration. And why it is happening? Because of increased exchange energy. To remember, the shortcut is for yttrium, zirconium and cadmium, you have 5s2. You have 5s2. For palladium, you have no electron in the 5s. For remaining all of the elements, you have 5s1, 5s1, 5s1 only. So if 5s1 is the electronic configuration in the S subshell, automatically you can fill the number of electrons in 4D. Yes or no? Automatically you can fill the number of electrons in 4D. Is that clear, students?
Yes.
Yes, sir.
Yes, very good. In the 5D series, if you look at the differences, wherever you have 6s1, there you have the exception. Yes or no? Because 6s2, 5d1, 6s2, 5d2, 6s2, 5d3, 6s2, 5d4, 6s. What is the n plus l value? N plus l value 6 plus 0, that would be 6. 5d, what is the n plus l value? 5 plus 2, that would be 7. So 6s was completely filled, then only 5d has to be filled. So 6s to 5d1, 6s to 5d2, 6s to 5d3, 6s to 5d4, 6s to 5d5, 6s to 5d6, 6s to 5d7, and here in the platinum and gold, you have 6s1, 5d1, 5d, 6s1, 5d9, 6s1, 5d10. These are the exceptions. Write down this. You may again ask a question, sir, why are you not writing for 6s2, 5d4 configuration? Why are you not writing as 5d5, 6s1? You can ask, right? Because in the 5d5, you have half-filled electronic configuration. In the 6s, in the 5d5, 6s1, you have half-filled for the 5d subshell, which is more stable generally speaking. But that is not happening here in the 5d series. Why? Why? Because here after lanthanum, you have F subshell filled. F subshell filled. F subshell is having even more shielding effect. Yes or no? The poor shielding of F subshell, that is the reason for the lanthanide contraction also. So that is why these are the exceptions seen. So 5d1, 5d5, 6s1, that is not there. 5d4, 6s2 is the electronic configuration possible in the 5d series. You can compare this with 3d and argue like, why can't you are getting similar to 4s1, 3d5? Why are you not getting 6s1, 5d5? Because here in the 5d series, you have lanthanides. In the lanthanides, the 4f subshell is filled. The 4f subshell will have poor shielding. Yes or no? Because of that poor shielding effect, the exceptions are going to be deferred. Understood, students? Clear or not?
Yes, sir.
Clear?
Yes, sir.
Right, very good. So these are the exceptions what we see in the electronic configurations of D blocks, and those are the exceptions. Like in the D5 configurations, we have seen the exceptions in metallic bonding, enthalpy of atomization, and melting point. Now then comes the next important point is atomic radius or atomic radii. If you try to look at the graph, first you look at the graph, you will get an idea. Yes, from this graph, what you can say, students? So obviously this green line is the 3D series, the yellowish line is the 4D, and above that you have 5D. You are taking radius on the y-axis and you are just increasing the atomic number in the x-axis. So if you look at this atomic radius, how is the atomic radius varying? Generally, how the atomic radius varies in a particular period? If you go from left to right in a period, how the atomic radius should vary? Atomic radius. From left to right in a period, how the atomic radius should vary? General case. We do have exceptions.
Decreases.
Decreases. Why?
Force of attraction between the nucleus and electron.
Because of increased effective nuclear charge. Yes or no? Nuclear charge, because you are going in the same period, electrons were added in the same subshell, so the protons were added more. So because of more number of protons, the outermost electrons are attracted greatly. Because of increased nuclear charge, the size is going to be decreased. That is the general case. That means we have a nucleus, we have an atom, at the center of atom we have nucleus. We have first shell, second shell, third shell, like this we have different shells. And let us say this is the outermost electron. And in the same outermost shell, you are adding the electrons. If you are looking at the period, like period 2, you consider period 2, 1s2, 2s1, 1s2, 2s2, 1s2, 2s2, 2p1, 1s2, 2s2, 2p2. That means you are adding the electrons in the same second shell or not. If you start from lithium and go to neon, so on, you will get 1s2, 2s2, 2p6. You are adding the electrons in the same second shell. You are adding electrons in the same second shell if you go from left to right in a period 2. But protons are increased. Because of increase in the protons, obviously the positive charge of the nucleus increased. That means nuclear charge increased. So that is going to be attracting that increase in nuclear charge will attract the outermost electron. So size should decrease. So what is the general point, students? Size will be decreasing if you go from left to right in a period because of increase in the effective nuclear charge. That's fine. But now you look at the graph. This is experimentally observed. This is experimentally observed graph, which is completely true. Experimentally observed. So the experimentally observed things are true. That is what happening in reality. So whatever the theory we have, we should frame our theory in such a way such that it will explain the reality. This is experiment means that is the real situation. So in reality, how the atomic radius is varying? Starting from scandium, if you look at a 3D series, starting from scandium to manganese, what happens? You can see the decrease in the atomic radius. We expect the decrease only, so that's fine. After manganese, we have iron, cobalt, nickel. There you have almost same radii, almost same. Then after nickel, you have copper and zinc, where you can see the increase. That means from the first element to the middle of the series, what is happening to the atomic radii? It is decreasing. Then after, for the rest of 3 elements, it is going to be same. And then after, for the last 2 elements, the atomic radius is increasing. So how can you understand this variation in atomic radii? How we can understand this variation means, if you observe carefully, you have, this is not a period 2, right? This 3D series, 4D series, 5D series, they are not period 2. They are 4th period, 5th period, and 6th period. You look at the electronic configuration of 3D series elements. You have 1s2 completely filled, like any 3D series element you consider, starting from scandium. How you can write? 1s2, 2s2, 2p6, 3s2, 3p6. This is completely done. So first shell completely done, second shell completely done, third shell you have 3s, 3p, 3d, fourth shell you have 4s. Look carefully, students, very interesting. So which is, in the first shell you have 1s, in the second shell you have 2s, 2p, in the third shell you have 3s, 3p, and 3d, in the fourth shell you have 4s. First electrons are filled in the 1s, 1s2 completely filled, no issues with the 1s2. Second shell 2s2, 2p6 completely filled. Second shell 2s2, 2p6, no issues with the electronic filling. Third shell, in the third shell we have 3s, 3p, 3d, 3 subshells are there. In the 3s electrons are completely filled, in the 3p also electrons are completely filled. But after filling 3s to 3p6, the electrons are entering which subshell? After filling 3s2 and 3p6, the electrons, next electrons were filled in 3d or 4s?
4s.
4s.
4s. So 3d is there. Yeah, 3d is 0 I am writing as of now. In the 3d we are not filling electrons. 4s, in the 4s we have to fill 2 electrons. After filling 2 electrons in the 4s2, then you get the 3d series where the 3d subshell is filled. Now you look at the filling of electrons. You are filling electrons in the 3D subshell, which is the inner shell or not? This is not the outermost shell. Is that point clear?
Yes,
to
sir.
you?
Yes, sir.
Yes. Yes, fine. So in the 3D series, you are filling the electrons, that's fine. But where you are filling the electrons? You are filling the electrons in the inner 3D subshell. Because of the filling of electrons, what will happen? Obviously, electrons filled means protons are also increased. Protons increased means outermost. Which is the outermost shell now? 3D or 4s? 4s is the outermost shell. Yes or no? 4s subshell is present in the fourth shell, which is the outermost shell. You are not filling electrons in the outermost shell in the 3D series. You are filling electrons in the inner 3D subshell. Because of filling of electrons, obviously nuclear charge increased. So because of increase in nuclear charge, the 4s electrons were attracted towards the nucleus greatly. But you have one factor is increased nuclear charge. Increased nuclear charge. This is one factor. The other factor is because of filling electrons in the inner shells, that is inner 3D subshell, these electrons in the inner 3D subshell, will they repel the 4s electrons or not? Yes or no?
Yes, sir.
Look
Yes.
the
Yes, sir.
4s, yeah.
Yes.
Look at the 4s electron. The 4s electron is attracted greatly toward the nucleus because of increased nuclear charge. Look at the same 4s electron. The 4s electron is repelled by the electrons from the 3D subshell. That means the 4s electrons are experiencing two types of forces. What are those? One is the increased nuclear charge, so nuclear force of attraction. Yes or no? The electrostatic force of attraction between nucleus and the outermost electron. The second one is the repelling or electronic repulsions. Electronic repulsions from inner 3D electrons. Inner 3D electrons. So if you go from scandium to the middle of the series, that is up to manganese, which is the dominant factor? The repulsions or the nuclear charge? Size is
Nuclear.
decreasing. Yes or no? Size decreasing means which is the dominant factor? From scandium to manganese, Z effective is dominant. Is dominant. From iron to nickel, the effective nuclear charge and the electronic repulsions, they are balancing each other. That is why size is not increasing or decreasing. Size is same. From scandium to manganese, the Z effective is dominant. So size decreases. Next, from Fe to nickel, Z effective is balancing with or is balanced with repulsions. Repulsions. So same size. So same size. Right? Finally, from copper to zinc, more number of electrons are present. Where you have more number of electrons present? Because in the copper and in the zinc you have very high number of electrons present. Because of very high number of electrons, repulsions are going to be the dominant factor. Because of that, size increases. Aditi, what's your doubt? Any doubts, students, so far?
No, sir.
No, right? So simple logic, students, you don't need to complicate at all. When you are going from left to right in a period, atomic size decreases. That is the first point we need to know. Why it decreases? Because the nuclear charge increases. But in the D block elements, if you look carefully, you are filling electrons in the 3D subshell. which is the inner subshell. So the outermost electrons were attracted towards the nucleus because of increased nuclear charge. The outermost electrons were repelled by the inner 3D electrons. So these are the two factors which are present. What are two factors? The increased nuclear charge is one factor, and the other factor is inner electrons repelling the outermost electrons. Inner electrons repelling the outermost electrons. Because of these two factors, the size will be decreasing from scandium to manganese. Then you have equal size from iron, cobalt, nickel, and then from copper to zinc, the atomic size will be increasing. Is that clear to you? Is that clear or not so far?
Yes, sir.
Right?
Yes, sir.
Very good. Now you try to answer this question. Among a 3D and 4D, which will have more size? Very simple question. Among a 3D series
4D.
and 4D, yeah, very good. Among 3D
4D.
4D.
series, very good, all of you. Among 3D series elements and 4D series elements, which will have greater size? Obviously 4D series, because there you are filling electrons in the, you are filling in the 5s, fifth shell also, which is going to be larger when compared to third shell or third 3D series elements. Among 3D and 4D, you say 4D is greater. Now say among 4D and 5D, which is greater?
5D.
Among
5D.
5D.
5D, very good. But look at the difference, students. 3D is somewhere here, that is fourth period. Then you have 4D, fifth period. Then you have 5D, sixth period. 3D to 4D, what happened to the size? This is size, no? Size has been increased greatly or not? But 4D to 5D, what happened to size? Size is increased, but can you say that increase is great or very, very less, or it is matching with the 4D directly? From 3D to 4D, from 3D to 4D, the atomic size or atomic radii that should be increasing, that's sure, because the electrons are entering the next higher energy subshell. From 4D to 5D also, atomic size should increase, generally speaking, because the electrons are still entering the next higher energy subshell. But if you look at the sizes of 4D series elements and 5D series elements, there is no much difference. They are almost the same. Why is it so?
DD transition.
Okay, DD transition is one answer. Anyone else?
Lanthanide
S
contraction.
electron.
Very good. Lanthanide contraction. Right. So let us understand what happens in the lanthanide contraction. Yes, Suman. Okay, look carefully, students. 3D to 4D, great increase in size, great increase in size. But 4D to 5D, very less increase in size, very less increase in size. This is due to poor shielding of inner 4f electrons. Inner 4f electrons. You can imagine this lanthanide contraction in this way. You have nucleus, first shell, second shell, third shell, fourth shell, fifth shell, sixth shell. So you have 6s2 here. You have 5D here. You have 4f here. If you look at the 5D series elements, 5D series means what? 5D series means which period? Sixth period. Sixth period means you should be filling the electrons in the 6s, outermost electrons. 6s2 you have filled the electrons, but After filling 6s2, that is after lanthanum, you have lanthanides, that is where 4f subshell is filled. After 4f, again you are filling the 5d, right or not? So after 6s, you are filling electrons in the 4f in the lanthanides. After lanthanides, you fill electrons in the 5d. Now listen carefully. What is the shape of s orbital? Spherical. P orbital, dumbbell. D orbital, double
Double
dumbbell.
double.
And f orbital, complex in nature. What happens when you go from S to P, P to D, D to F? What happened to the dispersion of electron density? Increased or decreased? Dispersion means spread out. The electron density is spread out greatly or not?
Yes, sir.
Now understand, this is your nucleus. It is attracting the outermost electrons. Outermost electrons means 6s electrons. Outermost electrons means 6s electrons. The inner electrons are there, they are going to repel, that is also known. That is why size is decreasing first, then equal for 3 elements, then it is increasing. That's fine. But if you look carefully, there are inner 4f subshell electrons. Like you can say, this as your arrow, the nucleus as an arrow, and your 6s electrons as a shield. 6s electrons as a U. You are just imagine yourself in a war. You are fighting the enemies, and enemies are throwing arrows at you. Here, what is the arrow? Nuclear charge. And to protect yourself from those arrows, what do you have? You have a shield. You have a shield. So if I have a shield, I'll take my shield and protect myself from the arrow. That means the arrow, it cannot hit me now directly because the inner electron, because the shield is protecting me. Same thing, the inner electrons are shields. What are the inner electrons? Inner electrons act as a shield. What is your arrow? Arrow is the nuclear charge. Inner electrons are your shield. Who are you? You are the outermost electron. Now imagine you have the shield, but your shield has a lot of holes. Why I am saying your shield has a lot of holes? Because your inner electrons are filled in the 4f subshell, which is dispersed greatly. Which is dispersed means which is spread across in space greatly. Electron density in f subshell can be present somewhat like this. That means you have an arrow. You have an arrow which is coming towards you, and you also have a shield, but your shield has a lot of holes. The probability of the arrow to hit you is high or not? Because the inner electrons has a lot of holes, the nuclear charge can directly attract you. That means the arrow can directly hit you. That means you have the inner electrons, you have a shield, but that shield is a very poor shield or not? Because it has a lot of holes. So because of the shape of 4f subshell, because of the shape of f orbital, the f orbitals are dispersed in space. They cannot shield the outermost electron. So the outermost electrons are attracted greatly toward the nucleus. Understood this point or not? Yes or no?
Yes, sir.
Okay, you are the yeah, very good. You are the outermost electron, just imagine. And your nuclear charge is the arrow. If the arrow hits you, obviously if nuclear charge hits you, you are moving closer toward the nucleus. But to protect you, what do you have? You have inner electrons. These inner electrons repel you, so they are protecting you from the arrow. But if the inner electrons are in the 4f subshell, what is the drawback you have? Inner electrons are there. That means shield is there, but that is very, very poor. Why? Because it is dispersed in nature. So there is lot of empty space present out. So the outermost electrons can be attracted toward the nucleus. Write down. This is due to the sixth period. That means in the 5D series, whatever the elements you have, they are going to have almost equal in size when compared to the 4D series. But 4D to 5D, very less increase in size. This is due to poor shielding effect, poor shielding of inner 4f electrons. Inner 4f electrons, write down this. Inner 4f electrons has dispersed shape, dispersed electron density, and that is why, the outermost electrons, are attracted, the outermost electrons are attracted greatly towards the nucleus, and thus size decreases, So 3D series, 4D series, 5D series, so size should increase, but 3D to 4D great increase in size is there, but 4D to 5D very small increase in size because of poor shielding effect of inner 4f subshell electrons. Is that clear, students?
Yes, sir.
Just 2 points you need to understand. What is the first point? Like in a series, in a 3D series, what happens? From the first element to the middle of the elements, from the first element to the middle element of the series, size decreases. Why? Nuclear charge is the dominant factor. Remaining 3 elements like iron, cobalt, nickel, size will be almost same because nuclear charge and electronic repulsions were almost balancing each other. For the last 2 elements, size increases. Why? Because repulsion is the dominant factor. So size first decreases, then equal, and then increases. This is a scenario with respect to one series. Now compare between 2 series like 3D, 4D, 4D, 5D. 3D to 4D, great increase in size. 4D to 5D, less increase in size because of lanthanide contraction. Right? So that is your point. So in the last 2 electrons, attraction between nucleus and valence shell electrons are less as compared to the repulsion between valence shell electron and the penultimate shell. That's why atomic radius from copper to zinc increases. The same points whatever we have discussed. Atomic radii of 4D series elements are more than 3D series elements, and 4D and 5D series elements nearly have same atomic radii. Why? Due to lanthanide contraction, which is due to poor shielding of 4f subshell electrons. Right, students? So this is about your atomic radius. Magnetic character. The next property is after metallic bonding, melting point, enthalpy of atomization, atomic radius, yes or no, and exceptions in the electronic configuration. The next property you need to understand is magnetic character. Metals which have unpaired electrons show paramagnetism. Can anyone say what is paramagnetic substance? How does that paramagnetic substance behave to external magnetic field?
Weakly attracted.
Harishri says weakly attracted. Very good. Others? Weakly attracted or repelled? Lakshmi Rani says having unpaired electrons. Very good. So species which have unpaired electrons, that is said to be paramagnetic in nature. That is true. But what does this unpaired electron do? That's the first point you need to understand. To understand about an unpaired electron, you need to understand about an electron first. What is an electron? You have an atom. In the atom, you have nucleus. Around the nucleus, you have electrons revolving. If you look at electron is a negatively charged cloud and it is spinning around itself. Look at the motion of electron. You have nucleus. My wrist is a nucleus now. You have electron. The negatively charged cloud is moving around the nucleus as well as spinning around its own axis. That is how electron is moving. This is how electrons are moving. Yes or no? The electron has what type of motion? Electron has orbital motion and spin motion. Electron has orbital motion and also spin. Electron, because of this orbital motion and because of this spin, like you can imagine the electron as a negatively charged particle. Negatively charged particle moving in a circular path. Can I say this as? Can I say this orbit as a current carrying loop or not? You have studied magnetism. You might be knowing about current carrying loop. Yes or no?
Yes, sir.
So
Yes, sir.
negatively charged electron moving around the nucleus, you can imagine that as a current carrying loop. The charged particle moving in a circular path, it's like a current carrying loop. Because of this current carrying loop, there is some magnetic field developed. So electron itself behaves as a tiny magnet. Understand this point carefully, students. Whatever the electron we have, the electron revolving around a nucleus, each and every electron revolving around a nucleus, it behaves as a tiny magnet. If one more electron comes in a orbital, how many electrons can be placed? 2 electrons. One electron is there, it has some magnetic field. The other electron, if it has a different spin, opposite spin, the magnetic fields are going to be neutralized. So whenever you have an unpaired electron, that unpaired electron behaves as a tiny magnet, it will develop some magnetic field. Because of that unpaired electron, because of that magnetic field of unpaired electron, if that species which has unpaired electron is taken towards an external magnetic field like a bar magnet, you have attraction of that particular species. Write down this. Metals which have unpaired electron show paramagnetism. Electron itself behaves as a tiny magnet due to its orbital and spin motion If we have an unpaired electron, its a magnetic field, it will be attracted by the external magnetic field, because the unpaired electron itself has some tiny magnetic field. You are applying some external magnetic field, so there will be some tiny attraction. So it will be attracted by the external magnetic field. These are very logical points. Okay, unpaired electrons wherever you have, they itself behave as a tiny magnets, so they are going to be attracted by the external magnetic field, which is like a bar magnet. So metals which have unpaired electrons, they show paramagnetism. And the spin only magnetic moment is said to be under root of n into n plus 2. What is n? N here stands for number of unpaired electrons. N here stands for number of unpaired electrons. Bm is Bohr magneton, the unit of magnetic moment. Mu is equals to under root of n into n plus 2 Bohr magneton. And if you look carefully, what is this called, students? Spin only magnetic moment. Electron, it behaves as a tiny magnet. I have told you, no. It behaves as a tiny magnet means it should have some magnetic moment. The magnetic moment will be again due to its orbital motion because it is orbiting nucleus. The magnetic moment can also due to spin motion because it is spinning around its own axis. The spin only magnetic moment is given by this formula under root of n into n plus 2. The orbital magnetic moment that is given in your atomic structure, we can study that whenever we look into the concepts of atomic structure. What is the total magnetic moment of the electron? The spin only magnetic moment plus orbital magnetic moment. If we have to combine these two vectors, which is out of your syllabus, you don't need to worry with that. spin only magnetic moment is under root of n into n plus 2 Bohr magneton. So n is the number of unpaired electrons, unit is Bohr magneton. For Cr plus 3, how many unpaired electrons are there? Cr plus 3. Write down the electronic configuration. Chromium means argon 3d5 4s1. Chromium plus 3 means you have to remove how many electrons? Chromium plus 3. Chromium plus 3 is obtained from chromium by removing how many electrons from chromium?
3.
3 electrons. How the 3 electrons are removed? Can I remove the 3 electron directly from 3D?
No,
No,
sir.
sir.
No, sir. Starting from 4s.
Yeah,
4s.
first you have to remove the electron from 4s, 1 from 4s and 2 from 3D. So argon 3d3 4s0. Yes or no? 3 electrons removed. So 3d3 means how many unpaired electrons are there? 1, 2, 3. So therefore, what is the magnetic moment? Magnetic moment is equals to under root of 3 into 3 plus 2 Bohr magneton. Do the calculation, you will get 3.87 Bohr magneton. Like you don't need to calculate the students. Whenever you have like 2 unpaired electrons, you will get the magnetic moment as 2.8 or 2.9. 3 unpaired electrons there means 3.8 or 3.9. 4 unpaired electrons means 4.8 or 4.9. Indirectly, you can say if the magnetic moment is 5.8 or 5.9, you can say number of unpaired electrons as 5. Yes or no? You can do the calculation and get the answers. But if they have given the magnetic moment as 5.8 or 5.9, then you can say number of unpaired electrons are 5. Magnetic moment 4.8 or 4.9, you can say number of unpaired electrons as 4. So number of unpaired electron 3 means you will be having some 3.87 or 3.9, that as a spin only magnetic moment, right?
Yes, sir.
Yes, very good. So this is how paramagnetic substances behave. So you have a weight, 2 weights, and here we have one substance placed, and you are bringing out the bar magnet now. Because of the bar magnet, what happened? Whatever substance placed here, that is attracted by the bar magnet. Initially, both the weights are same, but one side you have a paramagnetic substance. So I have taken a bar magnet on that side. So bar magnet is attracting the paramagnetic substance weakly. Because of that, it come down. So the other weight moves up. The other weight moves up. Diamagnetic means what happens? Diamagnetic means no unpaired electron. Diamagnetic means no unpaired electron. If there is no unpaired electron, obviously it is going to be diamagnetic. If there is no unpaired electron, obviously it will be repelled by external magnetic field. External magnetic field. What is the external magnetic field you are giving? The external magnetic field is supplied by the bar magnet. So you take the bar magnet now. Because of that, the external magnetic field, the diamagnetic substance has moved away. That means repulsed. So the other weight comes down. What about ferromagnetic? Ferromagnetic, can anyone say? Ferromagnetic is an extreme form of paramagnetic substance. Extreme form of paramagnetism. That means very strong attraction. Very strongly attracted by external magnetic field. We do have ferrimagnetic substances and antiferromagnetic substances. We will discuss those ferrimagnetic and antiferromagnetic in the solid states. Okay, ferromagnetic substances are those substances which will be attracted strongly by the external magnetic field, and the ferromagnetic substances, that is nothing but an extreme form of paramagnetism. That is nothing but a extreme form. You can write down here. When a magnetic field is applied, substances which are attracted very strongly are said to be ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetic nature. You can write down the example. Ferromagnetic materials are Iron, cobalt, nickel, metals. Metals are generally ferromagnetic in nature. Note down the students, note down this, note down this and let me know if you are done. Done or not? You can just type letter S in the comment section.
Done, sir.
Done?
Yes, sir.
Very good. Formation of interstitial compounds. After this magnetic nature and atomic radii, the D block elements also have a tendency to form interstitial compounds. Can anyone say what are interstitial compounds? Interstitial compounds. Like if you might have studied solid states, as I have told you or explained you in the metallic bonding, you have different crystal lattice sites. Yes or no? You consider any solid, any part of the solid. You have crystal lattice site. So here you have some ion, here you have some more, here you have some other. Like that, at different crystal lattice sites, you have all the ions placed. And if you look carefully, electrons are moving throughout the metal, that's fine. But if you look carefully, there are some interstitial sites. There are some interstitial sites, especially if you studied, if you remember from solid states, we call them as voids, tetrahedral voids, octahedral voids. Some empty spaces are there or not, students?
Yes, sir.
Yes,
Yes
sir.
or no? So after filling the respective particles in the crystal lattice sites, there are some empty spaces left out. Those empty spaces are said to be interstitial sites. If some of the small atoms like hydrogen, carbon, nitrogen, if they are trapped inside these crystal lattice sites or inside these interstitial sites, then you are saying that will lead to the formation of interstitial compounds. You can look at the animation here. You have the some blue dots present at the interstitial sites. Yes or no? So because of the placement of these atoms at the interstitial sites, you will be having a disturbance in the stoichiometry. The compound is not stoichiometric now. Like you can have compound like Mn4n, Fe3H, VH 0.56, TiH 1.7. There is no stoichiometry present. Why? Because of the occupation of the atoms like hydrogen, carbon, nitrogen at the interstitial sites, you can say the stoichiometry is disturbed and these compounds are non-stoichiometric in nature and they will having some examples of there are Mn4, Fe3H, VH 0.56. Stoichiometry is not present. And they are going to retain the metallic conductivity. Metals are conductors or not? All the metals are conductors, yes or no?
Yes, sir.
Why?
Yes.
Yes, sir.
Why? Keshav, why? Just answer, right or wrong, that's okay, fine.
Due to
Metals
free
are
electrons.
due to free electron, that's right, 100%, very good. Yes or no? Due to the presence of free electrons in the metal, the transfer of electrons is happening. So the free electrons are moving throughout the metal. That is why metal is a conductor. So because of the placement of these elements like hydrogen, carbon, nitrogen at the interstitial sites, are the free electrons disturbed? No, they are still present. No, because of the placement of these small atoms at interstitial sites, the free electrons are never disturbed. So they retain metallic conductivity. They retain metallic conductivity. And they have high melting point. They are pure metal. Why? Can anyone say why it is so? If I have an atom somewhere here, we have free electrons throughout. You have free electrons throughout. And you have smaller atoms like here. I'll change the color. Okay. Because of the position of the atoms at the interstitial sites, what is going to happen is these interstitial atoms, they are also going to be attracted by the free electrons. These interstitial atoms, they are going to be stopping the repulsions between the two metal kernels, because I have told you this is a metal kernel. Yes or no? Mn plus is a metal kernel. Mn plus is a metal kernel. Mn plus is a metal kernel. This is also a metal kernel. This is also a metal kernel. If we do not have an atom here, like the interstitial atom, the metal kernels are going to repel also. The electrostatic attraction is there between Mn plus and all the free electrons. But between two metal kernels, there is also repulsion or not? Positive charges repel. But if I place an interstitial atom like hydrogen or carbon or nitrogen, the repulsion between the metal kernel can be decreased slightly. Why? Because in this small atom also we have electron. Because of that, these metal kernels move away slightly. Because of that moving away motion, what is going to happen is repulsions decrease. Repulsions are going to be decreased, so they are going to have very stronger melting point than the pure metal. They have high melting point than the pure metal, and because of high melting point, they are very hard and they are chemically inert. If there is a particular substance which has very highest melting point, like diamond you take or gold you take, gold, diamond, they are used as a jewelries. Yes or no? Why? Because they are not reactive. If I wear a gold bracelet and if it is reactive with the environment, then what's the point of wearing a gold? Yes or no? Gold is not reactive to any other elements easily. It's only reactive under extreme situations. That is the reason why these are even used as jewelry. So because of that, because of the increased melting point than the pure metal, these interstitial compounds are very hard. If they are very hard, automatically they are going to be chemically inert, similar to that of your gold and diamond. Right, students, understood now the formation of interstitial compounds? Yes or no?
Yes.
Yes.
Yes. Yes, very good. So let us continue with our discussion. So let me change the slides. Do you know alloys? Can anyone define what is an alloy?
Combination of two different metals.
Very good, Kanishka.
Homogeneous mixture of metals.
Very good. Okay. So when two or more metals are combined, then they can be leading to the formation of an alloy. It is like a solid solution. Like if I have a glass of water, like here I have water bottle here. If I add some pinch of salt, what will happen, students? That pinch of salt will dissolve in the water. What I am going to have? I am going to have salt water. But for you, can you figure it out whether it's a pure water or salt water? Can you look at this solution and can say it is a salt water or pure water by just looking at? We can't say, right? Because it is homogeneity is there. The salt is dissolved completely. The salt NaCl molecules are completely present throughout the water. So we can't identify. That means there is some homogeneity. There is some homogeneity. In the same way, the homogeneous solid solutions, not like a solution, like not like a liquid solution, solid solution, imagine. Solids have crystal lattice. Now some of the lattice sites, if they are occupied by different other metals and it is looking like a homogeneous system, under that condition you can say the alloys are going to be formed. What are alloys means? Alloys are crystals of different metals. Crystals of different metals in a same solid. In a same solid. Or alloys are compounds where different metals are there in the same solid. You can just look at the crystal lattice structure of one particular species. So the white ions or white colored spheres you can imagine as copper, and the other color is zinc, a black color. You can have a metal like this. Yes or no? You can have a crystal structure like this. This crystal structure will be completely moving throughout, where all the copper atoms or copper ions are present at different crystal lattice sites. Some of the coppers can be removed from some part of the crystal lattice sites. You can look at the second animation now. If you look at the second animation, what is happening is some part of the crystal that is being lost from the copper atoms. The next part, what you are going to have? In the next part, you are going to have placement of all those crystal lattice sites by different metal like a zinc, copper and zinc combined now. Not only like this, you can have zinc placed in different other manners like the fourth picture also. Like you can have copper and zinc can be at any of the crystal lattice sites, and you are going to generate a crystal, complete crystal like this, which is an alloy, which is going to be your alloy. So what is alloy? Alloy is it's a crystal solid which has different metal types. D block elements has a great tendency to form alloys. Can you say the reason why? Why the D block elements have a great tendency to form alloys? Because of similar sizes. First and main reason is because of similar sizes. Write down this. Transition elements have maximum tendency to form alloys. The reactivity of transition elements is very less and their sizes are almost similar. Due to this, sizes similar, due to that only transition metal atom in a lattice can be easily replaced by other transition metal atom. If you remember from solid state, you may ask a question, sir, why are you always relating to solid state? Because all these D block elements, they are metals, they have a different crystal lattice sites. So they have different crystal structures. So we have to relate to solid state only. So if you look at a solid state, if you look at ionic solids, metallic solids, you are going to have, in the ionic solids, what do you have? You will have the cation or the anion forming of the lattice. The other ions, they are at the voids positions. If you look at an ionic solid, there comes the radius ratios, radius of cation by radius of anion. Based on the radius ratio only, we can say what type of crystal is possible or not. Yes or no? Radius ratio of cation to anion will give an idea, will give us an idea about the type of crystal lattice structure, about the type of crystal lattice structure in ionic solid, Similar to this, similar to ionic solid, in metallic solids also, the radius of metal ions or metal kernels will be the deciding factor for crystal lattice site, for crystal structures. You can simply say like BCC or FCC or HCP, what type of crystal structure is going to be present, that is dependent upon the radius of metal kernels. And if you look at the transition elements, the other transition elements also have similar radii. We have seen that radius from the graph only. Yes or no? If you look at transition elements, you have radius varying like this. Like copper here, zinc here, almost close radius, no? Because of close radius, the crystal lattice sites can be occupied by different kinds of metal ions easily. That's what they are meaning to say. The reactivity of transition elements is very less. Why? Because they are hard and their sizes are almost similar. Because of similar sizes, what happens? Due to this similar size, transition metal atom in a lattice, like here we have a transition metal atom copper in a lattice that can be replaced by other transition like zinc, which has similar radius, and hence they have maximum tendency to form alloys. And hence they have maximum tendency to form alloys. And these alloys, they have the ratio of component metals fixed, and they are extremely hard because of the alloys also you have increase in the metallic bonding. They are also extremely hard and have highest melting points. All of you note down the students. They are also extremely. Yes, Priya. Any doubts? Okay, note down. So alloys have very hard nature and they have high melting point. Why? Why? Because they are going to have strong metallic bonding. Why? Why? Because they are placed at some of the crystal lattice sites. Why? Why? Because they have similar sizes. The transition metals have similar sizes. Because of that, they can be placed in the crystal lattice sites easily, leading to the formation of alloys. And all this is depending upon size, radius of the metals. Is that clear, students?
Yes, sir.
Yes.
Yes.
Yes, very good. Yeah, transition metals form alloys because the major property or the major phenomenon is similarity of radii. It is a major or dominating factor. Dominating factor. And they also form alloys if they have, because they have same properties also. The properties are also slightly same. Some important alloys you write down, very, very important. All of you note down, memorize the marked alloys. Bronze. Bronze means you have combination of copper and tin. Brass means copper and zinc. Prachi, this one, same properties.
No, sir, before this one.
They are extremely hard and have high melting point. The reason is again simple.
Okay.
Why? Okay, why they are extremely hard? Because they are placed at some of the metal lattice sites. Obviously, the copper, if you have Cu plus ions present, they have electrostatic force of repulsion slightly. If zinc is placed, that can move this copper slightly away, minimizing the repulsions. Repulsions less means stability gained. Stability gained means hardness will be increased. Hardness higher, highest melting point. And also, what you can say, because of the placement of zinc in some of the crystal lattice sites of copper, the number of unpaired electrons increased because zinc gives how many electrons? Zn plus 2 electrons. It is giving 2 electrons. So because of the more number of electrons, you will be having stronger metallic bonding. Because of stronger metallic bonding, they are also extremely hard. Understood now, Prachi?
Yes, sir.
Yes. Memorize this, all of you. Bronze means copper plus tin. Yes or no? Brass means copper plus zinc. Gunmetal is copper plus zinc plus tin. German silver is copper plus zinc plus nickel. If you want, you can write down. In the German silver, you have copper varying from 50 to 61%. You have zinc varying from 17 to 19% composition, and nickel varying from 21 to 30%. This is a scenario or composition of German silver. In German silver, you do not have silver. And gunmetal, German silver composition. Gunmetal composition also write down. In the gunmetal, what do we have? 88% copper will be there, 10% tin, and 2% zinc. Write down this, all of you. Bronze and bronze compositions are not required. They are actually alloys of copper and tin. Bronze is an alloy of copper and tin. Brass is an alloy of copper and zinc. Gunmetal is an alloy of copper, zinc, and tin. And the compositions I have given here, you write down these compositions. And German silver, it is a alloy of copper, zinc, and nickel. And compositions you can write down. Copper is 50 to 61%, zinc is 17 to 19%, nickel is 21 to 30%. Right? Is everything clear so far, students?
Sir, compositions are asked
Yes.
in the exam.
You have to remember, actually these compositions were given in metallurgy. There's a chapter named metallurgy, if you remember. There the compositions were given. So we have to remember. Okay. Clear, Prachi?
Yes, sir.
Yes. And if you look carefully again, students, the D block elements or the transition elements, they have a tendency to form complex compounds. Why? Because of their small size. Because of their small size, can you say they have more charge density? What is density? Formula for density?
Mass upon volume.
Mass by volume, very good. What is charge density? Charge by volume. Yes or no? Density is nothing but mass by volume, right? Charge density, if I'm asking, charge by volume, only slight change. They have small size. Small size means volume is small or not? Because of small size, because of small size, their volume is small. Because of small volume, they will have high charge density. That means the same charge present in a very small region of space, it has a greater charge density. Because of greater charge density, it will attract. If a metal ion is there with great charge density, it will attract the oppositely charged metal ions greatly. And because of this high charge density, they are going to form complexes. And along with these two, small size, high charge density, there is an availability of vacant orbital. In a 3D series, or 4D series, the vacant orbitals are available. The vacant orbitals are available which can accept electrons, from the ligands. You know ligands? What are ligands? Ligands are electron donating species. We will discuss what are ligands in your complex compounds in detail. As of now, you can just note down. In the vacant orbitals, like vacant orbital present mean, then only they can get electrons. If there is no vacant orbital, electrons cannot be occupied. You cannot say that. So all of you might be wanting to go to a very good university. Yes or no? So let us say AIMS, you all want to go to AIMS. So what is AIMS doing? AIMS is attracting all of you. Attraction is different. Acception is different. Acception means there should be some vacancy. In the AIMS, if the vacancy is high, then only it can accept you. Similarly, the metal ions, they are positively charged. They are attracting electrons. That's fine. Every metal ion can attract the electron. But every metal ion cannot accept the electron. For a metal ion to accept an electron, there should be some vacant orbitals. Electrons should come and go into the vacant orbital. And they have vacant orbitals, the d block elements. That is why they are forming the complexes easily. Right, students? So they have a tendency to form complexes, d block elements, due to small size, high charge density, and availability of vacant orbital. We will discuss in the next class what type of complexes are formed and other properties of d block elements like catalytic activity, electrode potentials, all those things. Fine. Okay, students, thank you all. Bye.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.
Thank you, sir.
No, sir.
Thank you, sir.